So starting with a power supply of 5 volts, this is our circuit that we have built of circuit 1 of the NPN transistor. So we're going to measure the voltage between ADJ and ground. Which is 4.98. Earlier we had measured about 4.96. Now we're going to measure the voltage between base and ground. This is about 0.711, around 0.7. Now we're going to measure between the collector and ground. This is around 188.2 millivolts, so around 0.188 volts. And then to find the change in voltage of RB, we would do 4.96 minus 0.707, because here RB is the voltage change between VADJ and base, so we would subtract VADJ, we would subtract base from VADJ, and we got 4.253. And then to measure the change in voltage of VRC, we got 4.812. This is from the voltage change of RC is between 5 and the collector, so we do 5 minus 0.188, and we got 4.812. And then to calculate the milliamps of IB, we know that V equals I times R. We have our RB of 100K, so we would divide 4.253 divided by 100K, and we got 0.04253 in terms of milliamps. And then for IC, again using V equals I times R, we would do, we have our resistor of 1K, so we would do 4.812 divided by 1K, and in terms of milliamps, this is also 4.812 milliamps. Now, when our VADJ was around 1.9 and 2.6, our VRC ended up being 2.04 and 3.01. And this is quite far from 5, which means our transistor is not saturated yet, which shows that the multiple of the ICs and the IBs is around 163 and 161. But once it was saturated, it dropped to 128. So here we have a graphing the relationship between IB and IC. And we see that from 0 to 3.7, the relationship is roughly linear, but as it reaches 5, which is the max voltage that the transistor can have between collector and emitter with no current IC, the graph starts to flatline, and the slope becomes smaller, which is as seen by the multiples that we have calculated between IC and IB, and they start to become smaller and smaller. And this is because it's reaching its point of saturation, the 5 volts. So even though IB is increasing, IC can't increase because VRC can't hit the limit of the 5 voltage circuit. So first, just to verify our measurements made on this bottom row where VADJ is at 5 volts, we'll measure out this again. So to measure out VADJ, it's at 5.00. We had it at 5.01 earlier. And to measure V base, .717. We also had 0.717 earlier for V base. Then to measure out V collector, we're at 1.77, very close to 1.78. And to find the change in VRB, we would subtract VADJ from V base to get 4.293, and to find change in VRC, we would subtract 5 from 1.78 to get 3.22, And then to calculate the current IB and IC, we would use Ohm's law, V equals IR, where V is the change in voltage here, 4.293, divided by the resistor value 100K to get 0.04293. And then for IC, we would do 3.22 divided by the resistor value of 470, which is different from our last circuit, which is why we get values increasing. So here we have a combined graph with RC 470, the black line, and then RC 1K, this slowly flatlining line in gray that we use with RC equals 1K. So unlike our last circuit with RC 1K, our IC is increasing linearly and not flatlining unlike here, while IB is increasing even when V80J equals 5 volts, because our VRC is not nearing the saturation point of 5V, because at V80J of 5V, our VRC is still 3.22 volts. So here we're going to measure all our voltage values when the temperature sensor is heated up. So starting with VLM34, we have a value of 0.876 volts. And then going to VC, we have a value of 3.297. So this means that to calculate the change in VLED, we would do 5 minus 3.297, which is about 1.7 volts. So in this next table, since we don't have a blue LED, we're going to use a green LED. And then now we're heating it up again. We're going to measure the voltage values, starting with LM34. We have a value of 0.85. Then going to VC, have a value of 2.816. So this means that our change in VLED would be 2.184 in comparison to the numbers when they were, the measurements when they were cooled, 0.54 when it's at LM34, 2.9 VC, and change in VLED would be 2.1. So it is valid for an increase in temperature to let the LED become brighter. And here we're heating it up. We're still heating it up, and it's much brighter than it was when we cooled it down. And this is because the voltage of LM34 is increasing, which also means that V base is increasing. And we know that VE equals VB minus 0.7. So VB increases, and so does VE and IE. And we know the equation IC equals IE times B divided by B plus 1. But if B is so large, then this part of the equation, just B divided by B plus 1, reduces to 1. And IC equals IE times 1. So IC equals IE. And if IC equals IE, therefore IC has increases because we just said that IE is increasing. Therefore, a stronger current is flowing through the LED, so it becomes brighter.